Okay, chapter 6.1, discrete random variables. So first of all, let's talk about a random variable. It's a numerical measure of the outcome from a probability experiment. So its value is determined by chance. Random variables are denoted using letters such as capital X. Okay, there's two types of random variables, discrete and continuous. Discrete random variables has either a finite or countable number of values. Okay, the values of a discrete random variable can be plotted on a number line with space between each point. A continuous random variable has infinitely many values. So these values can be plotted on a number line in an uninterrupted fashion like an interval. So everything in between 0 and 4. So this is the same definition that we talked about, the distinction between discrete and continuous previously. Can you have 1.5 values of your variable? Then it's not discrete. Okay, so on this section, we're going to focus on discrete. Okay, determine whether the following random variables are discrete or continuous. State possible values for the random variable. Let me get my pen. The number of light bulbs that burn out in a room of 10 light bulbs. Okay, well, can you have 2.5 bulbs burn out? No, either your bulb burns out or it doesn't. So it's discrete. And possible values, you could have no bulbs burn out, or 1, or 2, or 3, or any number up to 10. But you can't have 20 bulbs burn out in a room that only has 10 bulbs in it. Okay, the number of cars in the McDonald's drive-thru. Can you have half a car in a drive-thru? No. So this one's discrete. And once again, it could be empty, or there could be 1 car or 2 car or 3 cars, or any number of cars. They could, pile up around the block, I presume. Okay, the length of time between calls to 911. Oh, that right there, length of time. Remember we used that before about talking about continuous. Can you have half a minute in between calls? You bet. So this is continuous. So let's talk about it in terms like they did on the previous one, in terms of a number line. And so there could be no time between calls, right? They could come in at the same time, okay? Or they could come in 30 seconds apart, 1.5 minutes apart. How come that? There we go. 5 minutes apart, 10.5 minutes apart. Actually, I guess technically, it doesn't say in a day. I was going to say up to 24 hours. So it could go 24, but this doesn't say in a day. Okay, because the value of a random variable is determined by chance, we can assign probabilities to the possible values. So remember what our probability distributions meant. The probability distribution of a discrete random variable provides the possible values of the random variable and their corresponding probabilities. A probability distribution can be in the form of a table, a graph, or a mathematical formula. So the table to the right shows the probability distribution for the random variable X, where X represents the number of movies streamed on Netflix each month. Okay. So the number of movies offered on Netflix being 0 happens 6% of the time, right? If they offer 2 movies a month, 22% of the time, or 0.22. Notice Netflix is not going to have half a movie up. Okay. Remember our rules for probability distributions. That's going to hold here also. First of all, the sum of the probabilities has to equal 1, and each individual probability has to be between 0 and 1 inclusive. No negative probabilities, no probabilities greater than 100%, obviously, or 1. So is this, okay, is this a probability distribution? Well, they're all probabilities between 0 and 1. Let's add them up and make sure that the sum equals 1. So 34, 56, 66, 96, oops, that adds up to 0.97, right? So no, this is not a probability distribution. Okay, is this a probability distribution? Oh, this one's real easy because look right here. So no, this one is also not a probability distribution because I can't have individual probabilities less than 0 or more than 1. Okay, so remember, just because you see what's being called a probability distribution table, make sure that we verify that it actually is. Okay. Draw a probability histogram of the probability distribution to the right, which represents the number of movies streamed on Netflix each month. Okay, first of all, let's make sure it's a probability distribution. So 58, there's 86, 96, 97, 98, 100, all between 0 and 1. Okay, so this is just like when we were drawing histograms before. This horizontal axis are your data values, and your probability or frequency is on your vertical axis. The difference is in a discrete probability distribution, we want to include horizontal lines going across from each value because that really emphasizes that we're talking about these are discrete values. It's that are allowed. Also remember, we describe distributions from their shape, and so this one would be skewed right. Okay, if I drew this curve over the top of it, skewed right. Okay, but we also, when describing distributions of a variable, we talk about its center and its spread. So we're going to use the mean to describe the center and the standard deviation to describe the spread. So the mean is given by this formula. And once again, it's just this times this, plus this times this, plus this times this. Okay? So compute the mean, get my pen back, of the probability distribution to the right, which represents the number of DVDs a person can rent from a video store. And notice the use of mu, right? We're saying this is the population. This is 100% of the data. So no videos happen 6% of the time. One video gets rented per visit, 0.58. 2 times 0.22 plus 3 times 0.1 plus 4 times 0.03 plus 5 times 0.01. All right, so I'm just going to enter all this in my calculator. So what do we have? Let's see, 0 plus 0.58 plus 0.44 plus 0.3 plus 0.12 plus 0.05, and we get 1.49. Okay, so notice that our answer here is not a possible value of the random variable, right? It's just you can't go in and rent 1.5 videos. Okay, this would mean like if I went in the store and rented 1, and you went in and rented 2, then the average rental for that day was 1.5 videos per person, but it's not necessarily a value. Also, from now on, we're going to follow the practice of rounding the mean and the standard deviation to one more decimal place than the value of the random variable. This one came out exact, so I didn't have to round. But I don't want to round that to 1.5, because if this would have been multiple decimal places, I would have rounded it to 3 decimal points. Okay, we're going to round to one more decimal place than the value of the random variable. Oh, so let's do round this to 1.5. I'm sorry, I was looking at the wrong one. One more decimal place than the value of the random variable, not the probability. Okay. Now, suppose an experiment is repeated some number of times and the value of the random variable is recorded each time. As the number of repetitions of the experiment increases, the mean value of the n trials will approach mu sub x. Okay, in other words, let x sub 1 be the value of the random variable after the first experiment, x sub 2 be after the second experiment, and so on. Then our sample mean, if we add up all our experiments and divide by how many we did, it's going to get closer and closer to this. In other words, the difference between them gets closer and closer to 0, so they get closer and closer together as the number of experiments increase. This is the same thing as our law of large numbers that we already talked about, right? Okay, so for example, the following data represent the number of DVDs rented by 100 randomly selected customers in a single visit. Compute the mean number of DVDs rented. Okay, so if I'm doing a sample, this is sample data. Okay, and notice, let's see, 1, 2, 3, 4, 5, 6 times there were 0 DVDs rented. They must have been out of whatever was popular, right? And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 4, 5, 6, 7, 8, 9, 41, 2, 3, 4, 5, 6, 7, 8, 9, 50, 1, 2, 3, 4, 55, 56. 1 was rented 56 times. Okay. 2 was rented 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22 times. 3 was rented 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times. Okay. 4 was rented 1, 2 times. And 5, whoops. And 5 was rented 1 time. Okay, so I suggest you find some way to keep track of your values here. And notice I can tell right away I missed one. So I need to update this number to 7. Okay, another way that I can tell that is I better add these up. 56 plus 7 is 63. 93, 85, 97, 98, 99, 100. Before I updated that, I'd have gotten 99. Now, but because this one told me 100 people, I would know something's off. But what if it didn't tell me and I just had a list of values? Yeah, I gotta go count them. But just find some way to keep up with, make sure you've accounted for every value. And then if we enter this in our calculator, okay, remember you need those parentheses to make sure all that stays in the numerator. We would have 56 plus 44 plus 36 plus 8 plus 5 divided by 100. We get 1.49. Now notice that's the exact mean that we got earlier, but in reality, what we're trying to say is when we have a lot of, experimental data, it's going to get closer and closer to that mu value, that theoretical value. Okay. And here we've got a graph that's kind of, all this is doing is just kind of explaining the law of large numbers. We're at 0 trials. Now they've put a line across here, the 1.49, okay, basically 1.5. That's our theoretical mean, okay. And at 50 trials, look where it is. It's about right here. And it gets closer and closer and close. Oh, sorry guys. And it gets closer and closer and closer to that mean. Now in the beginning, when you just have 1 or 2, it might hit it exactly, boom, boom, be really low. Just a couple of trials, it's all over the place. And then the more you have, the closer and closer and closer it's going to get to that theoretical mean. Okay, because the mean of a random variable represents what we would expect to happen in the long run, right? That's what that means, what you can expect to happen. It's also called the expected value. And here's the notation for the expected value. Okay, so the mean is the expected value. And we just saw how to calculate expected value. This times this plus this times this, right? Okay, but I want to go into a little more detail on this expected value. A term life insurance company, a term life insurance policy, will pay a beneficiary a certain sum of money upon the death of the policyholder. These policies have premiums that must be paid annually. Suppose a life insurance company sells a $250,000 one-year term life insurance policy to a 49-year-old female for $530. And this doesn't mean that she's got to die that year. Right, it's just a one-year term life. They're paid once a year. According to the National Vital Statistics Report, the probability the female will survive the year is 0.99791. So that's what this is. Let's forget this for a minute, but here's the probability that she survives. Meaning, if she does not survive, it's 1 minus this. So this is where this number came from. 1 minus that. Okay, so compute the expected value of this policy to the insurance company. Now, here's the amount of money that the insurance company gets. Okay, and so that's the expected value we're actually computing here, is the amount of money the insurance company can expect to get. Okay, now, if the woman dies though, right, then she paid them $530. But her estate's going to get $250,000. So the insurance company's actually going to lose $249,470. Okay, so one way we can do this is we can say, well, this is 530 times 0.99791. Okay, plus negative 249,470 times 0.00209, and add that all up. Okay, let's see what we get. Okay, 530 times 0.99791. And it's 249,470 times 0.00209. And we get 7.5 if we add that up, right? Don't forget that's a negative. They're losing money. Okay, so first of all, let's think about what this means. Okay, this means that the company expects to make $7.50. Since we're talking about money, let's put it in context. $7.50 for each 49-year-old female client that it insures during that year. Okay, this is the long-term result. It does not mean it's going to make $7.50 on every policy. On most of them, it's going to make $530. But every now and then, it's going to lose $249,000. But in the long run, over time, they can expect to gain $7.50 per policy. So if they can sell 1,000 policies, they'll make $7.50 1,000 times. In other words, $7,500. This premise does not work with only a few insured. That's why insurance companies have to insure thousands upon thousands of people. Okay, let's look at this from a different viewpoint, because this is the way I do my expected values, and sometimes it's not quite as apparent to do it like this. So just another viewpoint, right? We could say, okay, I'm going to do it like this. The expected value is that insurance company is going to make $530 100% of the time, right? Because it's every time it sells a policy, 100% of the policies it sells, it makes $530. And then it's going to lose $250,000. How much of the time? This amount of time. Okay, let's put that in our calculator. 530 minus 250,000 times 0.00209. Oh, same thing. Same thing. Okay, so a couple of choices there. Let's look at another example of expected value. In the Cash 5 lottery in Connecticut, a player pays $1 for a single ticket with 5 numbers. 5 balls, numbered 1 through 35, are randomly chosen from a bin without replacement. If all 5 numbers on a player's ticket match the 5 chosen, the player wins $100,000. The probability of this happening is 1 out of 324,632. If 4 numbers match, the player wins $300. This occurs 1 out of 2,164 times. If 3 numbers match, the player wins $10. This occurs with probability 1 out of 75. Compute and interpret the expected value of the game from the player's point of view. Now, this is important too. We're going to talk about this in just a minute. But right now, let's just compute that expected value. And here's what I was saying. Here's the way I do my expected value. Because if not, right, I don't have to account for this really being, he's going to win $299, and this person's going to win $99,999. This person's going to win $9, right? I can just say, hey, now this is from the player's point of view. So that player is going to pay $1 every single time, 100% of the time. Excuse me, let me get a drink right quick. That it plays the lottery, right? Lose $1. But it's going to win $100,000, 1 out of 324,632. And the player will win $300, 1 out of 2,164 times. And the player will win $10, 1 out of 75 times. That's the expected value to the player. So let's plug that in our calculator. So we get -1 plus 100,000 divided by 324,632 plus 300 divided by 2,164 plus 10 divided by 75. Okay, so I got -0.41999. Okay, but since we're talking about money, we'll say this is, okay, -42 cents. So it says compute and interpret. That means, on average, in the long run, that this player, if he keeps on playing this game, he's going to lose, or buying lottery tickets, he's going to lose about 42 cents for every time he buys. That's if he buys a ticket every week, you know, and he buys hundreds and hundreds of tickets. On average, he's going to win every now and then, right? A little bit of money every now and then, but mostly not. And he's going to lose about 42 cents a game, a play. Okay, now notice this said from the player's point of view. We could have done the exact same thing except from the game's point of view. The only difference would be the game is going to get $1 100% of the time, and then it's going to have to pay $100,000, pay $300,000, pay. So now this would be positive. Oh, the game on average is going to make about 42 cents every time it's played. And think how many millions of lottery tickets are sold. So it's going to be 42 cents, millions and millions of times. And every now and then it's going to have to pay out $100,000. But on average, in the long run, the game would make 42 cents. Not on each ticket. Okay? Does that make sense? Okay, standard deviation. So the standard deviation of a discrete random variable is given by this formula, okay, where x, of course, is the value of the random variable, mu sub x is the mean, and p of x is the probability of observing that. So we've got a formula here, but also our calculator will do these for us. So let's do that. Okay, computing the variance and standard deviation of a discrete random variable. Okay, compute the variance and standard deviation of the following probability distribution, which represents the number of DVDs a person rents from a video store during a single visit. Remember that remember the mean that we found was 1.49. Okay, that really doesn't matter. We could have also found our mean on the calculator, right? Okay, so let's talk about that. And once again, in the technology tips from the textbook, I think that's what I called the module, it'll have these instructions. But what we need to do is go into our stat and edit. And I've got some stuff in here, so let's clear out my list 1. Remember, to clear it out, you've got to move up, move your cursor up till it covers that L1 and hit clear. And then when you move back down, it'll be clear. Move over and do the same thing for L2. So in list 1, I'm going to put 0, 1, 2, 3, 4, and 5. And then I'm going to move over to list 2, and I'm going to put these values, 0.06, 0.58, 0.22, 0.1, 0.03, and 0.01. Okay, then we're going to go back to stat, excuse me, over to calc, hit enter for that one variable stats, and tell it that you want it to use L sub 1. So that is a second, and hit number 1. Notice again the yellow L sub 1 above number 1. Don't forget your comma. The newer calculators, you don't enter this way, and I think the instructions in the technology tips from the textbook are referencing if you have a newer calculator, it's a little bit different. But if yours is older, you hit a comma, and then you put the second L sub 2 in there, and hit enter, and it brings up all your stats. Notice that very first thing it brings up is the mean, right? 1.49, which we found by hand a while ago. So technically, we could just plug that in our calculator. But I'm looking for the variance and the standard deviation. So I'm just going to scroll down, and notice then I have a sigma x, right? That's our standard deviation, the sigma symbol for population. Okay. Also notice that S sub x is blank because this isn't a sample, it's a probability distribution. Anytime this equals 1, it's not going to give you that sample x because it's saying, oh, this equals 1. This is a population. This is my entire set of data. Okay. So sigma is 0.9327. Okay, remember, this is 1, so I'm going to put it at 0.9, 1 decimal place more than our values. But I wanted to leave several decimal places here because to find my variance, I'm going to have to square that. Okay, so now I'm going to go back to my regular calculator and say 0.9327 squared. And it's going to tell me that's 699 or 0.9. Okay, so notice if I had not left several decimal places here and I just took that 0.9 and squared it, I'm going to get 0.81. 0.9 squared is 0.81. Which would round to 0.8, not 0.9. So make sure you leave several decimal places in the middle of your calculations when you're, doing intermediate calculations. Okay, let me know if you need anything.